Okay, good morning everyone. Uh, well, you might have guessed, like, slow morning, slow starts, everybody tired from parties. But we're starting with the first scaling talk, EIP 4844. So I'll introduce myself. I'm Proto. Thank you, Liam. I work at OP Labs. This is the engineering arm of Optimism. And with OP Labs, we're building scaling solutions for Optimism itself, but also for Ethereum in general. And so this talk is specifically about one EIP that we're helping push forward to try and make the data that all these rollups use a lot less expensive and higher capacity. So I'll give some introduction what this EIP really is about in depth, the motivation, but then we'll get into the weeds, like how the EIP works, how we're going to achieve the scaling, and well, how this integrates in like the future of Ethereum. So what is data availability really about, right? So this is like the primary scaling bottleneck for Ethereum today, where, or maybe we have gas limits, right? Where we have state bloat that we kind of have to maintain, but to layer 2 we're already way past that. We have a new state, we don't have the problem of bloat as much, but we do have this capacity problem, where 90% or more of the transaction cost is going to basically to pay for gas for call data. Call data is like this inefficient form of no pruning, a very roundabout way to go get data into Ethereum, and we can optimize this. And so why do we need this data? This type of data needs to be available because the data is changing at a very fast pace, faster than a community can securely agree upon in a permissionless way. Say if you have a layer 2, the main scaling you get from the layer 2 is enabled by basically separating the job of the sequencer from the job of securing the data. You get this opportunity where now you can sync and acquire what you need to verify the chain in a way where the sequencer doesn't have this direct influence, where you can basically say, like, the layer 1 provides the data, if the data is not available, the layer 2 is not moving. And yeah, so as a challenger, this way you're always able to challenge the sequencer who might not be helpful in providing the data themselves. So a rollup is basically data availability and execution. Well, you have different types of rollups. You also have ZK rollups. Optimistic rollups use fraud proofs, 2 flavors. I'm sure you're already familiar with those. But just for introduction, we're an optimistic rollup. We're an interactive game type of rollup. The non-interactive game has largely been deprecated. Optimism started with a non-interactive game. I can answer questions about that after the talk. And then later today we have a talk about Canon, which introduces the interactive game, which enables arbitrary execution to be fraud-proven to scale Optimism with new tech. Anyway, so the differences between data availability and data retrievability, or like this long-term availability type of thing, is exactly the time of availability. You'll want the data to be available for a sufficient amount of time to challenge the sequencer, to build the state that's able to construct the fraud proof. But you don't need the data to be available forever. The Ethereum already kind of have an assumption that data older than a year, like, you can probably find it somewhere, you can probably sync it to some point. You don't need to go all the way back to Genesis. And after the merge, we reached this pivot point where even core developers from the Geth team are arguing that we should have some kind of snapshot approach or some kind of thing to try and make syncing sustainable, because we cannot always grow the amount of data in the chain without pruning. So with EIP 4844 we have a very similar construct where we want to prune the data, and since in this case the data only really needs to be available for a sufficient amount of time for honest actors to join the network, get the full state and challenge the sequencer, a month or somewhere on that order of magnitude, maybe 3 months, should be sufficient. So that's what EIP 4844 is built around. So a few years ago, 2020 and 2020, we had this insight from Vitalik, a few other people. Obviously, rollups were already getting in their initial shape. A few examples in the past. And Ethereum is basically going to be rollup centric. Why is it going to be rollup centric? It's because the complexity type of separation, where Ethereum itself, you don't want to grow and grow and grow in this complexity because it's not maintainable. People are going to argue about it, poor decisions will be made, and Ethereum will fail. Rather, you separate the complexity, and you separate execution from data, and you get data just right and very stable. And so rollups are basically the execution layer that's more innovative, more free to do what you want and not have to ask the layer 1 core developer community for permission. And this is why rollups move this much faster than layer 1. So modular blockchains is really about encapsulation, and well, it enables us without scaling. So some more introductions to EIP 4844. We have the classic chain today, ETH. We have this thing, this idea that we can separate consensus and execution. First separation in Ethereum, first modularity. So it'll look a little bit like this. Things are starting to get better. We have separate teams for different problems. API is really simple. 2 pieces of software. Josh today will talk about how Optimism is adopting a very similar design to try and encapsulate the complexity of the rollup and encapsulate complexity from Gav. And that way we can stay aligned with Ethereum without having to fight different incompatibilities. And so this is what Ethereum kind of looks like with fraud proofs and validity proofs. Fraud proofs have a little bit of a delay, but the idea is the same, where you attach this layer to EVM as an execution layer and you maintain the existing execution layer. But the kind of problem is it's awkward because you can stack execution, but you don't gain much efficiency. We need a data layer. So this could look like this, simple data provider and then the actual separation. Oh. And then we have our competitors, which are doing just that, but they don't even have a data or an execution layer on layer 1 at all. They have this concept of a sovereign rollup where you have proofs or you have fraud proofs or validity proofs. They have to be adjusted. They can't just work just like Ethereum layer 1, but they kind of just run out of band and they try to keep everyone on the same page. But you might have guessed bridging and composability gets a lot harder. So what do we propose? 4844 is trying to add data to Ethereum without breaking composability, without breaking this idea that we can have an execution layer on layer 1. So we add data, and then, well, I said before I continue, I should give credit to some more people here. So it's named, it's named after me and Dankat, but really, like, there's many more people working on it now. Big shout out to Carl working on KCG ceremony. Trent Mofi from OP Labs is basically pushing forward implementation. We have Michael from Coinbase working on a fork of Gav, continuing the prototype work that we started in Denver. And then we have consensus specs work with George, Xiaowei, Dankat of course, Vitalik, the crew. So what will it look like? This is what it will look like when we separate all these layers. So we have our consensus layer of layer 1, we have our execution layer of layer 1, then we add a data layer, and then we have layer 2. And then with Bedrock, with Optimism, we also modularize this layer. We split this also up into like a layer 2 consensus type of layer and a layer 2 execution layer. So what do we gain from this? We gain this encapsulation where we can now focus on one problem as a team, and we can independently scale these layers. And while the EVM is not hitting as much of a bottleneck right now, data is. And so this is what we need in the next year or so for Ethereum to scale. So how do we add this data? Data is really a blob. It's just an opaque, like raw byte string. And it is attached to a transaction. And a transaction makes its way through the Ethereum system just like any other transaction. But the attached contents have this additional lifetime. Where we have regular transactions, we have some rollup operator that incorporates the regular transactions. Then we have these batches that would normally be submitted straight to layer 1 with call data, but now we can use blobs. So we embed the blob data instead. We have a blob transaction, and the blob transaction is just the transaction that pays the fee, includes a commitment to efficiently prove any data might exist within that blob, but the data itself is separated. It's a sidecar. And so the sidecar can have a different lifetime than the call data. The call data lives with the execution payload. This is like a regular layer 1 transaction, whereas the blob is stored on a consensus layer. So it's stored in like a Prism node or a Lighthouse node instead of Geth. And these consensus layer nodes can prune it after a certain amount of time. So how does this look visually in the network? We go from layer 2 through layer 1, back to layer 2. So the sequencer produces data, we confirm the data, we move the sidecar from one pair to another in the network. We have execution going to an execution node, to a Geth node. So the fee payments happen there, the composability, the bridging, everything happens there. But the data that rollups need to verify go to other pairs in their database, and then these sidecars can be downloaded by layer 2 verifiers to sync the layer 2. Okay, so how does this transaction look like? The transaction consists conceptually of very similar things as an EAP 1559 transaction. Exact same thing there, but then we have this reference, these pointers to the blob contents, and then we have the separate blob contents. So these can then be separated into the sidecar. So as a transaction in a memory pool, you still want to provide the data up front, otherwise the transaction is kind of meaningless. But then after the fact, after it's been confirmed, you separate the fee payment, you keep that in the execution world, and you separate the blobs, put that in some like 1 month type storage for layer 2. So I can get into the nitty-gritty details. I think the main takeaway is that it's similar to EAP 1559. It adds this one addition, and we use this new fancy cryptography called KCG, which is this commitment scheme with polynomials. So you can represent your data in such a way that you can do an opening instead of a Merkle proof to get any amount of data and at any random positions in one constant size proof. So to use this type of thing inside of a rollup proof, we also gain a lot of efficiency. Okay, so how does the transaction processing actually work then? Well, transaction, inner blob transaction with fee payments and these references. The message is processed by the EVM. The commitments and the blobs live somewhere else in a sidecar. Liam.
Can you move slightly over time a bit so we can see the right half of the teeth?
Sorry. I'll slide over back because I'm afraid the recording will miss the screen. Right, so I have this indirection where transaction contents are split. And in this context in the EVM, we have this new opcode that provides this data hash, this version hash. And this thing helps you authenticate what's being confirmed with the transaction. So similar to the block hash opcode, which reveals what the commitment is to the block, so that you can do like a proof about block contents. Now you also have a data hash to prove something about data that's being included. And you just reference it relative to the transaction that you're processing. So you can by index, say index 0 or index 1, and then over time we'll increase the capacity or the amount of blobs that can be included with a transaction, so you can include more and more data. And then we have the engine API. After we process the fee payments in the execution engine and everything checks out, you will want to expose the result of not just the execution, but also the blobs that are selected to be included to the consensus layer, to the thing that decides that this proposal will be canonical and will be propagated to the rest of the network. So what we have is this bundle where we have our new data, and we have these engine methods that retrieve the data. And we have a get payload version 1 that we can change to version 2 to combine it with the existing API. Right now we prefer the separate methods because this nicely encapsulates the EIP in a way where we can add it to a client without making too many modifications. Over time we might want to try and combine the things, make it more efficient. And so this is the language that the Prism node and the Geth node talk to each other to exchange this kind of information for the EIP. So rollup integration. You might be thinking like, okay, we have data now. Like, how do we use it as a rollup in a secure way? How do we do fraud proofs over this? Or how do we do a ZK proof over this? So this is an example of a ZK proof. The ZK proof is quite extensive. ZK is not easy. And even here I'm simplifying it. This is part 1 of 2. What happens with ZK proofs is that today you have this call data, or you have some data that you can show something about, but then there's some complexity with EVM and some complexity trying to interpret commitments and trying to prove the data matches the commitment, and then figuring out some type of scheme to try and go from one commitment to the other commitment. This doesn't necessarily change. We still have some type of scheme where it's totally up to the ZK rollup to decide on like how they go from one state to the other state with their own choice of cryptography. But then we have this trick from Vitalik with a proof of equivalence. And the proof of equivalence says that one ZK commitment is the same as one other ZK commitment with a different scheme. And so you can say that the commitment native to the ZK rollup is the same as the commitment that we know with the EIP, the KCG commitment that commits over the data. And so using this commitment, you can show that certain data is getting included. So, okay, we have the proof of equivalence thing, prove the same points in ZK data accessed, then we verify the ZK proof, and then after verifying you'll need to do some persistence to get the ZK rollup to a state where the withdrawals and the state change can be recognized or persisted for the next transactions. Okay, so a simplified interactive fraud proof. I think interactive fraud proofs in this system are generally more elegant, but the core concept here is that with interactive fraud proofs, you can separate the source of data from the execution, and the execution just reduces to an interactive game, and the source of data is just a form of showing a pre-image or showing some data that matches the commitment or the hash that is confirmed in the layer 1. So this means that we have this pre-image oracle, this source of data that can be used during the verification of the steps in the game. And the opening to one piece of data out of this full blob is very similar to showing a pre-image of a regular hash, that you just show the proof and then it will be verified that it matches, and then through there you can make the data get included into the execution. Okay, so we have EIP 4844. After this we're not done with dunk sharding. This is just the first milestone. Dunk sharding itself also includes scaling in capacity beyond just like short-term scaling, where we have this kind of, we gain capacity by pruning, by having specialized data that doesn't touch on the EVM. But with dunk sharding we add sampling, so we can scale way beyond what a single node can process. So we're adding more blobs later. We add sampling, and then with dank sharding, we can get this even larger increase in data. And now we are talking about like things that are competitive with centralized chains, but now with Ethereum security. And the nice thing about 4844 is that we don't have to change anything about GAF after this. We are adding the transaction type, we're adding the market, we're adding the APIs. So all the work is done for the execution layer. And after this, it's only the consensus layer that will have to continue to evolve to introduce the full version of Dank. And this is your dream picture from the presentation, where we went through the ETH, we went through the merge, we went through several rollups, we went to EIP 4844, and then once we complete all of this, it will look like this, where we have many more blobs per EVM block, and all of these blobs in aggregate can be used by layer 2 solutions. And a layer 2 is not limited to just using one blob. Layer 2 can span over as many blobs as they want. And then, well, we'll get a lot more capacity in layer 2. So I'll talk a little bit about the development status. Like, this stuff is not all ready for production yet. We should talk about where we are at. And so I'll talk a little bit about the history, where we're at now, where we're going. So this is what has happened so far this year. The idea of mini dank sharding or 4844 was construed like around end last year, where we went for this like very naive call data cost change, and then we realized this is not sustainable. We want something better. And so Vitalik drafted up this proposal, like how to do a more minimal version of the full dank sharding plan, which became 4844. And then in February, Optimism helped them ship a hackathon type of prototype, something to get running, something to prove like the viability of the EIP. Then later, a week later, we drafted up the EIP, inspired by the draft from Vitalik and Dankrad. Then we added consensus specs, benchmarks. We started doing our first workshops. And well, more workshops, more calls. We're trying to integrate with many teams. And right now, it's not just anymore like this one team thing. Right now, we have people working on the KCG commitments, the ceremony required to support the new cryptography that we're introducing into Ethereum. But we also have a GAF fork, we have a Prism fork. Some people of Lighthouse are also working on this. And then, independent of this, there's a lot of spec work that needs to happen. And the hardest part here is versioning, trying to keep everyone in sync. And yeah, this is what we hope to help with and improve on. There's a lot happening, like it's hard to track, but we have a meta spec and other resources, so after the presentation you can find everything and maybe even contribute. So what's holding us back right now? I mentioned versioning. Versioning is one of those things. Like post-merge, EL, CL, these execution and consensus layer type of things, they have their own specifications and there's no existing process to collaborate between these two different layers. So this is what we are the guinea pig for, to like try and experiment. And individual repos, things that need to be synced. And once we are in sync, we can interrupt. We have a devnet that works. The other thing about syncing is that everybody is using this one BLAST library, but this BLAST library does not support the EIP yet. Instead, the prototypes are built with different libraries. So to support all of those clients, to sync them up with the EIP work, we need BLAST to support 4844. And what this really means is that they need to expose bindings and additional functions for some of the KCG cryptography. Then sync is another big item here, where you might have seen these discussions about optimistic sync, not to be confused with optimistic rollups. In the consensus layer, in the beacon node, we have this process where the execution layer, GAF, and the consensus layer, Prism, sync independently and then later consolidate to say we're fully synced or ready to continue driving the chain. Syncing here, if we're adding a layer, if we're adding this data stuff, we have yet another independent thing. It's very nice and optimized to run something in parallel, but it adds complexity and we need to specify this, make sure everybody is on the same page there. And then fee markets. Fee markets are also very fun. Fee markets are not unsolved. Like we do have an idea of like how EIP 1559 improves things. We can port over those ideas to the EIP. But right now the specification and the prototypes are all kind of out of sync. And so we will want to consolidate that. We will want to update the block header, simplify the data structure to implement EIP 1559 in like a minimal and clean way. So what's next? So yeah, like we should work on shared DevNet. Shared DevNets are basically this driving force to get new clients and new tooling, new things started for people to start testing and get involved. And this is exactly what OP Labs has been working on. Mofi from our team and Mikael from Coinbase have been working on this interop repository. So this exists already. We want to go bigger. There's more work to do. And so we need to sync these prototypes, we need to version things, and then we can involve more people. I'll tell a little bit about Bedrock, like how we plan to adopt EIP 4844. Right on time, Josh enters the room with the Bedrock talk. When we swap data, we can basically redeploy the next Optimism upgrade on EIP 4844 without too many changes. And so we can have the first rollup running on a testnet. This looks a little bit like this, where this is the existing system. A regular user only really runs a rollup node and an execution engine, and then they're connected to some RPC to acquire their layer 1 data. The batch emitter is something that Optimism as a protocol runs, where the data needs to become available. Proposer is this mechanism that submits the output route, which is like the state of the layer 2, so we can make withdrawals and other things happen on layer 1. So that stays the same, but then we have the beacon node that now hosts the blob data, so we're not putting data straight from the layer 1 execution engine, not from Gav, but from this other node. So combine the DevNet, combine the rollup, and we get into this like new experimentation phase where we can benchmark and productionize the dream to like get EIP 4844 ready for layer 1 deployment. So if you need more information, we have this thing called a meta spec. It's really useful for the developers around here, where it links to every other development resource and every other prototype, everything you might want to experiment with. And if you just want to learn about the EIP, there's this nice website, co-created by Liam, where you have learning resources, you have YouTube videos, you have an answer question type of thing from Vitalik. And so you can find other things there. And then I'm here for more questions. Let's talk. Josh, are we running out of time for your talk, or you want to start?
One question.
One question, or two questions.
Can you elaborate a bit? Can you go back to this slide with the batcher?
Yes. This one?
Yeah. So can you elaborate a bit about the batcher and the proposer?
I can, but we have a whole talk about that, so I didn't want to dig too deep into it, but Josh is going to cover that. I think the other slide is kind of useful. Where with Bedrock, we're redesigning this like processing. This used to be very monolithic in Optimism and other rollups, but now that we separate the concepts, we can traverse the chain, acquire the data, and include the deposits, all as like these separate functions. And so swapping this functionality becomes really easy. So attaching to an alternative data source is not that much work. Looking forward to that. Okay, thank you. One more question.
Really specific thing. What's the deal with BLST? Are they going to have this stuff? Do they know about it? When is that library going to be?
BOST, you pronounce it BLAST. It's a BOS library based supranational. The Ethereum Foundation is funding them in multiple rounds for different work, also VDF work and that kind of stuff. BLAST itself is a BOS library, very, very optimized, adopted by all the consensus layer clients, all the beacon nodes. And so this is pretty much the standard in performance and like auditing and like adoption. But it does lack a few of these functions that we need for KCG proofs to be efficient and like fit well into the beacon nodes. Because all this proof verification, it adds latency to verification and propagation of data. More latency is pretty bad. We need very fast verification to be able to be resilient against this denial of service type of attacks, large amount of data and bursts flowing into these nodes. The faster the better, that's what we need them for. That said, shout out to Mami, there's a developer from Nimbus writing Constantine, and in some areas, I can't say if it's in all areas, they're faster than Blast by making different trade-offs and doing a lot of these type of optimizations very well. Okay, let's dive into Bedrock.